Okay, Year 13, this is Application of Forces, Chapter 7D, and I'm doing this just in case people have got mock exams or are not in due to illness, and you have a reference point to go over this lesson. So it says here, read the question, you can solve problems about rigid bodies resting in limiting equilibrium. Now this important fact, if a body is on the point of moving, it is said to be in limiting equilibrium. In this case, the friction force takes its maximum value mu r, where mu is the coefficient of friction and r is a normal reaction. So we do know some of this. So we've got a uniform rod AB of mass 40 kg and length 10 meters. It rests with the end A on a rough horizontal ground, so hence we have friction. The rod rests against a smooth peg C where AC equals 8 meters. The rod is in a limiting equilibrium at an angle 15 degrees to the horizontal. Find A, the magnitude of the action at C. B, the coefficient of friction between the rod and the ground. So let's draw a diagram. That's 15 degrees. There's the smooth peg at C. So we draw a diagram and add all the things that we need to add. It's a uniform rod, so the centre of mass is going to be in the middle. So that's going to be mg, 40g. We have R, the normal reaction acting off the ground, and then we're going to get name this N, the reaction at C, because that's another reaction and we don't want to use the same letters. Okay, so the rod will have a tendency to slide downwards with the base moving to the left, because that would make sense, because it's away and it will want to move down. So friction will oppose this, so friction will go in this motion. That's how I started off. Now let's do a little parallel and perpendicular diagram. We know this is 15. Automatically we know that's 40 and 40g sine 15. Now we know here to here is 5 meters and here to here is 3 meters. Because the rod is 10 meters, so that's the centre of mass, and to the peg is 8, a total of 8. So the last bit must be 2. Now we have to take moments here, and that will help us find a normal reaction at peg A, so it's easier to take the moment from A. So taking moments about A, do write that down to make it clear. That's part 1 and part 2. So part 1, that's our centre of mass moment acting in the perpendicular direction, and that's going clockwise. So that's 40g cos 15 times that length 5, and that's going to equal 200g in total once we work that out, cos 15 Newton meters, and that's clockwise. We should be happy with that. And some F marks. Now this one, that combined length is 8 meters, and that's times n. So it's 8 n, and that, you can see, that's going to go around the clock, so that's anti-clockwise. So because it's in the limiting equilibrium, we know that they have to be equal, so we can form that equation. Just divide by 8 to solve for n. Calculate that using your calculator, and n equals 237. That's the first part, and this is a good recap of us with our moments. Now B, the coefficient of friction between the rod and the ground. So, important fact, this 40 sine 15 is not included as a moment about A, this because it acts down the rod, not perpendicular. You need to remember this. So it has a perpendicular distance of 0 and hence can be ignored. If you recap from what we learned in the past, so hopefully that will make sense. Now let's do our main skills, resolve horizontally and vertically to find the remaining forces. Let's split those up into horizontal and vertical components. So make another triangle, that's going to be 15. here, and we label like we do normally 230 sine theta, because that's the opposite, and hypotenuse, and we have that as well. Now, if it helps to understand why that's 15, well, if we draw a line across like this, there's an alternate angle 15 here. Anyway, the parallel and perpendicular components of the weight will no longer be needed, so we can get and remove that. So resolving horizontally, we have 230 sine theta, sine 15. Because it's the coefficient of friction between the rod and the ground. Resolve vertically now, that's up, we just have 237 cos theta cos 15 plus r equals 40g, because we have we're just resolving horizontally and vertically, hence we don't need the parallel and perpendicular components. Okay, because we've got this r, this cos, and that's got to equal 40. Rearrange this, so we have r as the subject, okay, now we're almost there. Now we know friction is at its maximum value, so F max equals mu r. Let's always write that down. We have r now, and we have F, which is the friction that we mentioned at the start. That's your F. And we just divide out by the bracket and we get mu equals 0.37. Right, if you're confident, try to see if you can give this question a go. And if you want me to go through another example, I will. I'm just going to go through a modelled answer because it will save some time. So, in this example, Dave just called that RC. Reaction at C, that might be easier. Now, because the rod is uniform of length 2 meters, our 60 newtons is going to be like so. So it's facing the other way, but diagram's still the same. So that's 15. Now remember, for moments we need the perpendicular, so that is going to be 60 cos 15, and this is going to be 60 sine 15. But remember, we don't need that for moments, okay, because that's going parallel to the plane. Right, so that distance must be 0.25, and here to here is 1 meter. So they've taken a shortcut because the rod remains stationary. Then we know the clockwise moment is going to be this 1.25 times RC. So I'm going to highlight that. Okay, that's our 1.25 times RC. That's going to equal our anti-clockwise moment, and you can write it separately to build up your skill, which is then 1 times 60 cos 15. Okay, that's our 1 times 60, because that length here is 1. Times not cos 15, it's 30. Don't know why I wrote 15 there. Times 30. That's cos 30. Now cos 30 is root 3 over 2. So essentially what we're going to get is RC times 1.25 is going to equal 60 times root 3 over 2, which is this working out here. So they've rearranged that to say equal to 0, but you don't have to. Now we get 1.25 RC minus 30 root 3 equals 0. And so we just solve that by bringing 30 root 3 and dividing by 1.25, and then we've shown that RC equals 24 root 3, like the question has shown. So always draw a diagram, or draw on top of the diagram, and that helps us. So for a rigid body in equilibrium, the resultant force in any direction is 0. And the resultant moment about any point is 0. That's why we can say they equal each other, or set it equal to 0. The way I showed you previously is just to build up the steps, which is better for your understanding. Right, I think we're going to be ready for the next part. So part B. The magnitude of the normal reaction force exerted by the ground at the point B is denoted by RB. So there's a normal reaction here, RB. The magnitude of the frictional force between the ground and the rod at point B is denoted by FB. So we have to note that down. Now, remember, that's your peg. So this would naturally slip down. So friction acts the other way. That's why friction is going this way. So by considering separately the forces acting in the horizontal and vertical directions, find the values of RB and FB. So you can see this question is scaffolded to build up your skills to answer these types of questions. So forces in the horizontal and vertical direction. So vertical is just up, and we're choosing up as positive. So RB, you can say actually equals 60 plus RC cos 30 because of our diagram here. Okay, that's the vertical. Or you can write it like so, RB minus 60 plus RC cos 30 equals 0. And I'll write that down to give us a bit more depth to that. So if you're just doing vertical, you can see what have we got vertically. We've got the RB. That's our RB. And our vertical here is RC cos 30. And sometimes we can write that, nothing wrong with doing it like that, RC cos 30, build up your skills, plus RB, so it's going up, equals 60. And hence that's how they got that's how they've got this line here to say it's equal to 0. But sometimes that's why I've done it. I would do it this way because it wants us to find the value of RB. So you can see their strengths and weaknesses to others. So this is just an easier step. So you can get 60 minus RC cos 30. Now we know what RC is from before, 24 over root 3, hence they've worked that out like so, and we get RB equals 24 newtons. Then we resolve horizontally, so this is vertical, change pen for horizontal, and this is probably how I would do it, horizontal. Let's see what we've got horizontally. We've got FB. Okay. And if we're choosing right as positive, then FB's got to be negative direction. But what have we got horizontally here? RC sine 30. So we're going to get RC sine 30 is going to equal RFB. Hence you can see how they get this line. RC sine 30 minus FB equals 0. Right, and you can see that's how I did it here, but from my step here we can just write FB equals RC sine 30. We know what RC is, and hence save us a line, work that out by substituting what so FB equals RC, which is 24 root 3 times sine 30, which is a half, and hence we get 12 root 3 newtons. Alright, now for part C, the coefficient of friction between the ground and the rod is denoted by mu. Given that the rod is about to slip, find the value of mu. So this is important. The rod is in limiting equilibrium, so the force of friction at B will have its maximum value. We know F max equals mu R, but it has to be mu RB. Okay. And so mu is just going to be our FB that we've worked out before, divided by RB, like so, and so mu equals root 3 over 2. I'll circle that so we can see this section. Alright, apologies, this is a bit all over the place, but I just wanted to fit everything on one page. Hopefully that makes sense to you guys. Okay, so in the Roy Monster, someone asked about going through ladders. Now this is a really tricky topic, so I found this question so it builds up our skill. Do pause the video and read it. I'm going to try and go through this quickly, but at least you have this to watch it over again once you get a better understanding of this topic. So this is very challenging to understand if you're not really secure with everything else in mechanics. Okay, so I'm gonna jump to the next page and we're going to talk about the answer, and this might be a bit easier, and I'm going to give us two examples, one straightforward one and one harder one. So you might think, why is RA here? Well, if this ladder is leaning against the wall, then you're going to get that normal reaction RA here, and this is leaning on the floor, so you're going to get that reaction RB. Now we've got the 5 meters because of the centre of mass, because it's probably likely to say uniform rod somewhere. Wonderful. So friction, ladder's going to likely slide down like so, so friction, it's not a force, so they just named that FF. Now you can see why they've got the weight W, because I just called it W. That's the weight, not the mass, so we do not need mg. So we know equilibrium means the resultant force in any direction is 0. So we're just resolving horizontally and vertically because there's no real moment here, nothing to twist and move about. at the moment because it just says horizontal and vertical, so we don't need to worry about moments. So what do we have horizontally and vertically? So depending on which direction, so they've chosen this as positive, that's resolving horizontally. So we've got RA equals FF, hence that's how we get RA minus FF equals 0. Okay, and now can you see how they've done it in reverse, so how I do it both ways. And then the vertical is the same. The vertical is, we've got this RB here equals W, so RB equals W, and RB minus W equals 0. Okay, same result. Okay, and that's what we've shown. RA equals FF, RB equals W. I think because it says show that, you have to start with this and go to here. Not too bad. We should understand that. Now this is the moments part. So B, again, moments about 0. So here we're taking our moments about B. So we have RA sine 50, right, and if you to work that out, okay, that's sine 50 here, that's our moment, and they've done it by working out this height, which actually is a method that works as well, just as easy. So that's why we get RA times 10 sine 50. That's going clockwise, that's clear. Now, it's perpendicular, remember, so we have to work that out. We know that angle is going to be the same, 50, and then we know that's W cos 50. Okay, so those equal essentially 10 sine 50 times RA, because that's the RA sine 50 and that's W, and that equals the anti-clockwise, which is W cos 50. If you draw the triangles, you will see. Okay, and so if we minus them, they equal 0. That's why they sent that out. But if we know our moments, we can see why we've shown this. Okay, so it says use our answers from part A and B to work out the value of mu. So remember, F max equals mu r. So in this case, that's our FF, and our normal reaction is RB. Okay, so it's going to be easier to work through that. Now, from the start of the question, lots of information. We know that W equals 34G, because that's the mass here, and we just called it a W to break up the skills. I've discussed this fact before. Now, we showed that RB equals W at the start, so RB must equals 34G. We showed that RA equals FF at the start, right, so RA must equal this like so, equals 34 G mu, and there's an easier way to substitute this. I'm not really the biggest fan of how they've done this. So now we can substitute this value for RA from B. So can you see we've substituted this 34G for RA here. Okay, and the W as 34G here. Now we can cancel out these G's and then solve for mu, and we get this answer. So mu is 0.420, which we know should be less than 1. So that's how we do that. Alright, so let's go to a more comprehensive example. And hopefully this helps us a lot. So do pause the video and have a read. Now I do have a ladder question that's a little bit challenging in one of my other videos. So this explains a ladder on the wall. Now these are challenging questions, but the aim is just to pick up some method marks where we can. So it's MB and it's a uniform rod, so it's in the middle. We've got the 2mg because a load of mass 2m is fixed on a ladder at point C where AC equals A, so A to C equals A. We get our normal reaction, they've just called it G here, but could be RA. That's our friction, and that's our friction because it's going to act the opposite way to the ladder is sliding. That's our reaction here, and you could easily call that RB, just have cleaner notation. That's A, 0.58 and 1.5A. That will make sense because the whole length is 3A, so this must be 1.5A for the centre of mass. We draw our triangles because we do also need to resolve perpendicular for the moments, and we do vertical and horizontal for this. So like all mechanics, it's resolving in these directions. We know it's mg cos 60. This is going to have the same, so that's 2mg cos 60. We've got to remember this point. We've got the triangle here as well. Now that's the opposite, so be careful. That's Rg sine 60. We've got 60, our right angle here. So we've got the diagram labelled all the forces. Both masses should be split into parallel and perpendicular components, and we do that for all questions. So let's take our moments about point A to give us a value of Rw. So moments from A. So this is just breaking it up. So we can see that's length A. This is clockwise. So that's A times 2mg cos 60. And that's our clockwise, and we've just cleaned that up a bit. Our second moment, now be careful, that's A plus 0.5A. So that's mg cos 60 times 1.5A. And we have that clockwise because that's going round in the clock. Now we know we've got our third one, and that's going anti-clockwise. That's why it's easier to split it up. I prefer doing it like this, arguably. And we know the clockwise is going to equal the clockwise. Okay. Those are the two clockwises together equals the anti-clockwise. Cancel the A's, we can divide out by A because A is in each term. So we get a new line like so. Now you're kind of starting to understand why you only need 56%, 55% for A level. Lots of steps. We group the terms together because we've got like terms. Cos 60 with mg's. So that's why we get 3.5 mg cos 60 and 3 Rw sine 60. Divide by 3 sine 60 to isolate RW, and we have RW like so. So we need to make a note of that. We can use that later. And it says calculate in terms of mg. So we're just going to work out this, type it in our calculator. We get a nice easy number to work with here. Right, so we don't know how to answer these questions, just resolve what we can. We can do some of these skills just to get some marks. That is crucial. Right, now we resolve horizontally and vertically because we need to do this so we can get RG. Alright, we found RW by doing moments, and that will help us find F as well. So same thing, resolving horizontally. Make that clear, guys. So you can see this is the positive direction, so F is going to equal RW. Boom, this is the way I like to do it. We already know RW so before, therefore we know what F is. Wonderful. Wonderful. So remember, F equals mu R. So F max equals mu R. So all we need to do is, we're almost there. We've got to resolve vertically next. So we've got our RG. We're taking up as positive. Should make sense. Equals, combine that 3 mg. Right, now we're almost there. As the ladder's in limiting equilibrium, we can use the formula for friction. We know F max equals mu R. Alright, we've got this R here, which we've got to use the RG. We know F equals RW, and hopefully that links with the earlier example I showed you where we had to do it. So we sub in the values. Alright, then we've got to isolate mu. Now if we divide out by 3 mg now, we can cancel out that. Alright, we should be happy with this stage. Divide by 3, and we have an answer for mu. Calculate it as 0.22, and we're done. Right, so that's some long videos and lots of listening, and you just need to practice this skill, and we will do some more questions on it. And I have a ladder video question in my mechanics section that you need to watch. I won't add it to this one because it'll just make it too